In this class, we can see another secondary effect that is called hot electron effects. So the secondary effect is due to the scaling down of channel length. So we can see that the progress in semiconductor integrated circuit technology can be attributed to the ability to shrink or scale the device. But the scaling down of MOSFET has a multitude benefits, but this will cause some secondary effects, and in that one of the most secondary effect is hot electron effect. So we can see that what is a hot electron and what is the hot electron effect. So we can see that when an electron travels from the source to the drain along the channel, so when an electron travels from the source to the drain along the channel, it gains kinetic energy at the expense of electrostatic potential energy in the pinch off region and become a hot electron. So we know that in this when an electron move from when we are applied a drain voltage, an electron will move from source to drains, and this electron gain energy, that means kinetic energy, and that electron is called as hot electron. At the conduction band edge, the electron has potential energy only. As it gains more kinetic energy, it moves higher up in the conduction band. So if it gets more and more energy, it will move more higher into the conduction band. So a few of the electron can become energetic enough to surmount the 3.1 electron volt potential barrier between the silicon channel and the gate oxide. Some of these injected hot electrons can go through the gate oxide and be collected as gate current, thereby reducing the input impedance. What will happen means, this hot electron, if we are reducing the channel, this electrons will get more and more energies, and that electrons are called hot electrons. So as it move from source to drain for ID, that will contribute current ID. In some of electrons get more energy and it will move more higher in this it will moves higher up in the conduction band. So a few electrons can become energetic to overcome the 3.1 electron volt potential barrier between the silicon channel and the gate oxide. So it will overcome that barrier potential, and that will can go through the gate oxide, and that will collected at the gate oxide, and that will contribute the gate current, that we and thereby that will reduce the input impedance. That means simply this means that if we are reducing the channel, what will happen, that due to the reduction in channel, the electrons get more kinetic energy as it moves from source to the drain, and some of the electrons will overcome the barrier potential between the silicon channel and the gate oxide, and few of them will move higher up the conduction band, and that electron some electrons that got this energy, more energy, that means that have the ability to overcome the barrier potential, will injected into the gate oxide, injected through the gate oxide and collected as gate current. That electron movement will cause current, current as it collected at the gate oxide, that current becomes gate current, and thereby reduce the input impedance, and that electrons are called, this more energetic electrons are called hot electrons, and this effect is called hot electron effect. So these electrons are trapped in the gate oxide as fixed oxide charges. So we studied that for ideal MOS there is no fixed charge in the gate oxide, it is perfectly insulated. But due to this hot electron effect, some of the electrons may trapped into the gate oxide, and that will contribute some fixed oxide charges. So what is the effect of this fixed oxide charge? Means it will increase the threshold voltage, that means it will increase the flat band voltage and therefore increase the threshold voltage. So in addition to this, this energetic hot carrier can degrade this MOSFET parameters such as transconductance, subthreshold slope, etc. So these are the effect of this hot carrier electrons. So one is the most important effect is increase the threshold voltage. So the solution to this problem is use what is known as lightly doped drain. So to reduce this, we need to use lightly doped drain. So we can see that, so this this is the scaling rules that we studied earlier. So we can see that what will happen means this is the electrons moving from source to drain, and in that some of the electrons will get higher energy, and that will move towards this try to overcome this outside barrier potential, and that will contribute gate current, and some of them will trapped in this SiO2 layer, and that will cause outside charging. So we can see that it will cause Panch-through effect, it will increase substrate current, it will cause it will degrade the subthreshold slope, and it will also increase the threshold voltage. So this is the short channel effect. So next we can see the change in threshold voltage due to this hot carrier effect. So this hot carrier effect will increase the threshold voltage. So we can see here this variation of current ID with respect to Vg before stress and after stress. So in this graph we can see that the threshold voltage requirement is increased for a short channel effect compared to long channel effect. So that is the effect of this hot carrier or hot electron effect for this threshold voltage. So that increase the threshold voltage requirement. Another signature effect of this hot electron is substrate current. That means as the electron travel towards the drain and become hot, they can create secondary electron hole pairs by impact ionization. So they get we said that for short channel this hot electrons are created, and it has more kinetic energy. So this electron will create another electron hole pairs by impact ionization. So the secondary electrons are collected at the drain and cause the drain current in saturation to increase with the drain bias at a high voltage. So that secondary electron hole pairs also contribute drain current. So that will increase the drain current. So we can say that that cause the drain current in saturation to increase with the drain bias voltage, and thereby leading to decrease of the output impedance. So this hot electrons or hot carrier effect may cause increase in the input impedance and decrease in the output impedance. So the secondary holes are collected at the substrate as substrate current. So the secondary electrons for an n-channel MOSFET, the secondary electrons are collected at the drain side, and that will contribute drain current, and the secondary holes will collected at the were collected at the substrate, and that will cause the substrate current. So this current can create circuit problems such as noise or latch up in circuit. So we can say that this hot electron have so many effects. First one is it will increase the flat band voltage, that means threshold voltage. It will increase the input impedance, it will decrease the output impedance, it will contribute ID, it will increase ID, it will increase substrate current, etc. So we can see the graph. So then this graph we can see that at saturation the current will increase, and this also cause the substrate current IB. So we can see in this figure. So this effect is called as hot electron effect. That means for a short channel device, this electron as the electron moving from source to drain, they get high kinetic energy, and they called hot electron, and they will try to overcome the barrier potential between the silicon and SiO outside interface, and some of these electrons may trapped at the interface also, and some of the electron will contribute gate current, and that will cause the threshold voltage requirement, as well as that will increase the input impedance. And similarly this hot electrons, this highly energetic electrons will provide secondary electron hole pairs by impact ionization. In that electrons may contribute more ID current, and the holes may contribute substrate current. So this is called hot electron effect.